Thank you so much for the invitation. Yeah, I've had a really good time. And so I'll tell you from some joint work with Megumi Harada and Christopher Manon, and then also a little bit about some companion paper by with my two co-authors and Adrian Cook, who was a master's student of Megumi Harada. Okay, so I want to start, and feel free to ask many questions. This is interdisciplinary, and this is, maybe I'm using fancy words, but it's understandable if you ask questions. So I want to start with telling you what toric degenerations are, and to start with that, I should tell you about toric varieties that we've seen in at least one talk this week. So if you start with a polytope that is a lattice or integral, and you look at all its lattice points, then you can construct a variety out of it by taking a monomial map. So you map x to the exponent vectors given by the lattice points, and you take the closure of that. So this is a map that we saw. If you want to see an example, you could think about Martina's talk. She was talking about this map, and she looked at the kernel, and she got an ideal that she was studying. So this is very much like the general case of toric varieties. And so there's a beautiful dictionary between combinatorics of polytopes, or geometry of polytopes, and the geometry of the variety. So for example, the dimension of your toric variety is equal to the dimension of your polytope. That's immediate. And volumes, if you're in polytope world, you like volumes. And the volume of a polytope, of the polytope, is also telling you something about the variety. It's roughly telling you how complicated your ideal is, and this is called the degree. So basically, if you intersect your variety with a general hyperplane of complementary dimension, it's telling you how many points you have in there. And of course, like, if you want to know more instances of the dictionary, you look at this big book by Cox-Littleschenk that is very big, and it takes a long time to read through it, but you will know many things about the dictionary. So we would like, this story is very much liked in algebraic geometry and combinatorics. For example, this dictionary has led to proofs of deep conjectures. And so we would like to have instances that we would like to generalize this to other cases. So if you start with a variety, it's probably not going to be toric. Is there a polytope such that you can approximate your variety using the toric variety, and thus use a polytope to approximate information or to know information of your variety? And so toric degenerations accomplish this. So a toric degeneration, so this is the definition, that it's technical, but I wanted to draw like a cartoon of what it is. So it's not going to be very exciting, but you have the origin, right? And you have a map, pi. And on top of it, you can imagine as you have a movie that at each point in C, on top of it, you have a variety. And so over here, on top of the 0, you want to have a toric variety. And then everywhere else, you want to have something that is isomorphic to X. Okay, so and so what this accomplishes is when you have a toric degeneration, you're able to approximate your variety X using the toric variety for the that toric variety that is called the special fiber. And in particular, you can use the combinatorics of the polytope of this toric variety to understand many facts about the original variety. So for example, the dimension of your variety is going to be the dimension of the polytope, same relation between degree and volume, and in general, you'll have that the Hilbert function of this variety is going to be the same as the Hilbert function of this variety, which isn't that is completely polytopal, and you can see the details in Cox-Littleschenk.
Can I ask a technical question?
Yes.
Are you really want the special fiber to be a toric variety on the nose, not
Yes.
a union of toric varieties?
No, I want it to be, yeah. Just, I mean, I'm only, okay, I should clarify I'm only going to talk about irreducible varieties here. So yeah, I guess that's a question. If it's not irreducible, you probably are allowed to have, yeah. But I won't go into non-irreducible. Okay, so this is a nice aim. Can you give techniques to construct toric degenerations? This is a big program in algebraic geometry and combinatorial algebraic geometry. So one way to do it is using Newton-Okounkov bodies. And so here, I'll give you the definition. I need to write this valuation definition for purposes that I want to use it later. So I'm going to start with an algebra. And you can think about it as the coordinate ring of a variety, or just C x1 up to xn modulo an ideal, a homogeneous ideal, because I want it to be projective. And then, so what does a valuation mean? So I want it to be a function. To the end, I guess. I just want to have these three properties on the board. And I'll give an example. Okay, so it satisfies these three properties. And what is an example? So it's basically like degree, you know, but it's more than degree, right? Because this is going to z to the n. And so my example, I'll draw here. So if you have a polynomial on n plus 1 variables, then I'm going to map it to the following. Just the first coordinate is going to be the degree of the polynomial. And then I want to take, so this should be reminiscent to Grobner basis. I want to kind of look at what is the like a leading term of this polynomial. And there's that little like, I'll say it in words, it's not too important. Like the order matters, of course. And for it, I just didn't want to have a -1 here. So for me to have a 1 there, I need something here that the degree should be in opposite order, but I don't want to dwell on that. Yes?
When you say the minimum, the order that you have on Z to the end is the lexicographic order?
So for this example, yes. Yeah, I'm going to take lexicographic. Usually I will take lexicographic. Yeah, but I guess it's not too important. You need to pick a total order, and it can be any order, but there's a theorem that basically everything can be thought about in lexicographic order. You don't get new theories by considering other orders. Okay, so now how do we, okay, so I want to obtain a toric degeneration, and I'm not going to give you, I'm not going to give you this type of picture, but I'm going to tell you what the toric variety is, and that's going to be the Newton-Okounkov body. So if I start with a variety of dimension d, and I pick a valuation, then the Newton-Okounkov body for this pair is going to be this. So you need to take the image of your valuation, and I'll draw what happens here. It's not super interesting, but it will be enlightening. You take the cone over there, you close it. You have to close it for reasons, but for this talk, you could ignore the closing because I won't give you the examples. And you intersect it with a hyperplane. So let's do that. So in this case, you're going to have that the image of your valuation. It's always a semi-group. Okay? And in this case, it's going to look like, so you have your three coordinates. Yeah, well, first, second, third, right? And then it's just going to look like okay. And And so what you want to do in this very, very simple case is you want to, so sorry, I shouldn't have drawn the lines. The lines is just to help me visualize it. But this is all on a plane. So then what you want to do is take the cone spanned by this. And in this case, and in this case, you don't have to close it. So you just take the cone spanned by this, and then you intersect it with this hyperplane. Where the first coordinate is equal to 1. And so you're going to get that your Newton-Okounkov body is this line interval. Okay? And so in general, yeah, the picture you can have for this these Newton-Okounkov bodies is you're always starting with a semigroup, you're taking a cone, and you're intersecting with a hyperplane. That's like the easy way to think about it. And so a theorem by Dave Anderson is that when the image, the image is a saturated semigroup, because sometimes you might be skipping some of the, like when you're generating the semigroup, you might be skipping some of the points in your lattice. So when it's saturated, you obtain a lattice polytope, and there's a degeneration to the normalization of the toric variety of this polytope. Okay? And so I often state this theorem imprecisely, but people here think about semigroups, so I wanted to say the semigroup part of it. So, but if you don't think about semigroups, then you can, the way to remember this is that is not correct, but it's a good way to think about it. If your Newton-Okounkov body is a lattice polytope, then you're going to obtain a degeneration. Okay? So this is a very much a black box, but the takeaway is that if you're able to find a valuation, and you're able to compute the Newton-Okounkov body, and you're in this wonderful situation, you obtain a toric degeneration.
So here, is it convex for the primitive generators?
The Newton-Okounkov body?
Yeah, that picture.
It's just this line segment.
Yeah.
So where's the degenerations usually involve a movie where you start with what you started with?
Yeah.
And what's the movie?
Yeah, in this case, so there's a machinery of associated graded. So it's hard for me to like tell you the movie per se, but there is a movie behind it. So I'm not gonna write for you the map, the flat family for you for this example, but associated in the machinery of associated graded, one can construct.
So many of us are more familiar with Grosvenor-Basses,
Uh-huh.
and I gave that exact description for Grosvenor-Basses in my thesis, that it is a flat family induced by one parameter subgroup, except that most of the time you get a monomial limit. But if you're really bad about choosing your order, you get something else which could be toric in the limit. But this is not that.
No, well, we
This
will
is not
see.
induced by a one parameter subgroup.
Yeah. I will give an example that is gonna it's gonna relate very nicely.
You
to
also
Grosvenor
talk in the language of
degenerations.
valuations, which Samuels and Mumford remembered, but basically was forgotten very quickly by the time I was even young. Okay, but most of us think in terms of weights and term orders,
yeah.
and then you pivoted to lexicographic order as if you are thinking in terms of.
No, yeah, exactly, and that is there's going to be a nice relation to tropical geometry coming very soon.
Yeah, and the other question would be Bernd-Sternfeld's camp. You're doing the Fulton camp of toric algebra. And the Bernd-Sternfeld's camp would say, form that ring, look at the kernel, that's binomials, and that's the toric ideal, toric algebra right on the nose. The slicing at x equals 1 is just a crutch. It's the ring right there.
Yeah.
But what does it have to do with initial ideals? I mean,
Yeah, we will get to that. Yeah, for sure. Yeah, I mean, I think in some sense, one danger of toric varieties, well, not danger, one beauty of toric varieties is that there's lots of ways to describe them, like polytopes, ideals, kernels of things, and it just, I like polytopes, as you can probably guess, so I probably always try to anchor it with a polytope. Okay, yeah, so I will tell you in the next slide, a connection with term orders. Because in general, constructing, not every, well, I don't know, that's a dangerous statement to say, but there are ways to construct, there may be ways to construct valuations that are not using term orders, but But I don't know, like my collaborator, Chris Manon, really believes that everything can be done using term orders. So I don't want to like make universal statements like that. But I do want to tell you a case where it's not going to give you all valuations, but it's going to be very Grosvenor basis for it. And this is a work of Kaveh and Manon. And what is beautiful about their work is that they give valuations that guarantee that you obtain a saturated semigroup and a lattice polytope. Okay, so we're going to choose a presentation for your coordinate ring. So as I said before, just ring polynomials, modulo, and ideal that's homogeneous. And you can construct that like this is the baby tropicalization, because there's very tropical experts here that would say like, oh, this is like the baby case. It's the baby case. So I just want to define a tropicalization of an ideal to be the weights such that the initial ideal contains no monomials. And so if you haven't thought about this before, this is in the tropical book, that this tropicalization is a fan where you can define the cones to be, you gather together all the weights. So you fix a weight and you want to see, well, which ones get paired with this one, all the weights that give you the same initial ideal. And then, so this is a beautiful breakdown of the tropicalization of an ideal into cones. And so for this example, the tropicalization of this ideal is going to be the product of a line, the line through 1, 1, 1, with these three rays. So it's hard to draw this. This picture is one-dimensional. It's not two-dimensional. People usually draw two-dimensional things and they say, this is filled in. No, this is empty. It's a one-dimensional picture. It's going to be the union of these three rays. Okay. And so in this case, if you notice, if you pay attention, and if you're really good at figuring out which ideals are prime, you will see that, well, this one is definitely not prime. Okay. Oh, and going back to before I go that way, here in your picture, if I looked at these maximal cones, you would be getting the initial degenerations would be monomial ideals, right? But I very much don't want monomial ideals because I want toric. I want binomial, irreducible binomial ideals.
But you have to restrict your valuations to get them.
Yeah. I mean, and the definition is a bit superficial because it's just, well, you'll see in a second. So one of these three, only one of these three ideals is prime. And as I said, if you're really good, well, this one is definitely not prime. But then between these two, maybe you're better at it than me. But only one of them, only this one gives you a prime ideal. Okay. So we're going to define a cone in the tropicalization to be prime if that initial ideal corresponding to that cone is prime. And so the theory of Grosvenor degenerations or initial ideals tells you that there is a degeneration from your original coordinate ring to the variety given by this ideal. And so what Kaveh and Manon do that is connected with Newton-Okounkov bodies. So if you start with a prime cone of the tropicalization and you pick a subset of the cone that is linearly independent, so it's a basis for the vector space spanned by C, you can have a valuation for your coordinate ring of your variety such that the Newton-Okounkov body is a polytope and the description is extremely concrete. It's the convex hull of the matrix with rows U1 up to UR. Okay? So this is a big family of valuations that are Grosvenor in flavor. And so, one starting point for this project was Megumi and I were wondering, well, this picture is not good because there's only one that is prime. But more generally, if you go to higher dimensions, or if you look at the Grassmannian, you will see the Grassmannian 2, n. You'll have that all the maximal cones give you prime cones. So you're going to have a bunch of degenerations arranged into a polyhedral picture, into a fan, into the fan that is the tropicalization. And so you have different degenerations. How are those degenerations related? And so a theorem of Megumi and I is that if you have two prime cones in the tropicalization that share a codimension 1 phase, so they're adjacent and they are giving you toric degenerations, then you can have a projection. So the polytopes are very similar. They only differ like in 1 dimension. So you have this picture. You have, this is one of the Newton-Okounkov bodies. This is another Newton-Okounkov body. And they both project down to this line segment. And I guess I could have drawn a 3-dimensional picture to make it more interesting, but then it may be hard to see. So it's always this two, the polytope on the top and on the bottom are the same when you project them down. And more importantly, because that I guess is not that exciting to me, what's more exciting is that if you look at the fibers of each of these maps, so you pick a point here and you look at the fiber over each of those two, you're gonna get intervals of the same length. So you can imagine you're arranging all these line segments of this polytope and you can like shift them up and down to obtain the polytope on the top. So we obtain piecewise-linear bijections between these two polytopes that are honestly just like shifting those line intervals up and down. So just because I like this theorem, I can do, we'll actually get two. One is the shift one that I'm telling you. So you move this line segment up here to the top, piece by piece. That's piecewise linear. And then the other one, well, it's gonna feel superficial, but of course, if you reflect this across the horizontal axis, you get two polytopes that project to the same lower dimensional polytope, and the fibers are of the same length, so they have the same relation. So at this stage, I can like shift up and down the line segments and get the piecewise linear function. And maybe you think this one is nicer because why would you reflect? But for the Grassmannian, this reflecting and shifting for the Grassmannian 2, n has connections, a very natural connection to cluster mutations. Okay, so 2 remarks that are important. So here is my same theorem by me and Megumi. So Nathan Ilton, in appendix to our paper, interprets these linear bijections as a generalization of the combinatorial mutations of Akhtar codes, Galkin, Kasprits, and that they appear in the study of mirror symmetry for Fano manifolds, especially toric cases. And so yeah, so if you look at our paper, we call it like what is it called? Well, anyways, I forget. I cannot believe I forget about the title of our paper. But because in the end, you know, we should have been calling it mutations, but we call it something else. So really, these maps should be called mutations because of this reason. Also because of this reason, because in the case of Grassmannian of 2 planes in Cn, as I said before, the reflect shift is connected to cluster mutations. Okay. So this is like a summary of what I've said so far. So if you start with a variety and you tropicalize it, then my work with Megumi, we give you a collection, well, together with anchored on the work by by Manon and Kaveh, we build a collection of Newton-Okounkov polytopes and piecewise linear bijections between them. So mutations between them. And this is like, these piecewise linear bijections, they don't just appear in our setting. You can also like do mirrors, like cluster algebras and varieties. They give you tropical degenerations, toric degenerations. I won't go into details, but it is known that cluster algebras are a way to construct toric degenerations. And in that setting, you again have polytopes and piecewise linear bijections between them. Yes?
When you say these piecewise linear bijections, are they also combinatorial mutations? So they are still formed?
Yeah. They are combinatorial mutations.
Okay,
Yes,
so
yes.
you're putting like many more polytopes into a flat family. Like you start with
So we will get to, we will be doing that because so far it's just like you have a notebook where you write, oh, this is one of the degenerations we have, change page. Oh, this is one of the degenerations you have. It's just like disconnected, except they're connected by piecewise linear mutations. But we want to connect, like, get more geometry out of this idea. So far it's just, yeah. Yes.
So, with the $1 million question, I mean, this mutations of polytopes is kind of reminiscent of, say, with the secondary fan when you form polytopes.
Yeah.
Is that the kind of dream you're looking for? Some sort of
Yeah.
global picture where all the mutations would fit in and you cross?
Yeah. And this is something that is very much of interest in mirror symmetry. So, and it's probably not going to be discrete. I mean, this is some that, yeah, $1 million question for sure. Can you understand all the toric degenerations? Can you tell me how to go between them? Can you understand, like, is that a beautiful space? What can you say about it? Yeah, for sure.
Does it have anything to do with scissors congruence for topology?
Oh, I've gotten this question before, like, and I haven't. Yeah, I like what Martina said. That I've gotten this question before, and I haven't sat down to think about it. I suspect the polytopes have scissors congruence between them, but yeah, but I don't. Yeah, I suspect the answer is yes, but not guaranteed. Yeah. Okay, so yes, so there's this $1 million question, and there's partial answers to it, like, is there a systematic theory that can unify them? And then I also, like, what I want to tell you with the rest of the talk is also something that I think, because there's a lot of ways to go from X to a collection of toric degenerations that are related in some way. But one of the things we're excited about is that we're proposing a viewpoint where we're starting with this data, not a collection of polytopes and piecewise linear bijections between them, and we're trying to go back to geometry. Just like in toric world, you start with a polytope and you go back to a variety. So to summarize what we're proposing, so here is kind of what Irem was suggesting. Well, we're going to propose a theory which generalizes the theory of toric varieties. In the theory of toric varieties, you have a single lattice and a single polytope. So we're going to replace the single lattice with a collection of lattices that are related by piecewise linear bijections or mutations. So this is going to be a movie, or a different sort of movie, I don't know. And then we're going to be able, so this is going to be more clear later, but I want to summarize it now, that we're going to replace, so in toric varieties, one way to think about it is you're compactifying, you use a polytope to understand how to compactify a torus, the algebraic torus. So we're going to have a similar idea where we're going to replace this ring, which is the coordinate ring of the torus, with an algebra, more general. And what is nice about this, some of the applications that we have, is that, well, okay, we generalize what we saw in Escobar-Harada, because in the Escobar-Harada, we just went from here to there, but as I said before, like, we're going to be going backwards. And we exhibit a collection of toric, like there's going to be families of families, but anyways, we will have a collection of toric degenerations of a single variety, and then each of those degenerations has a polytope, and each of those polytopes is related to the other one by mutations, by those mutations that we had before. Okay.
So this is fantastic, but I'm still lost. In Grosvenor basis theory, the degenerations come from a group action.
Okay.
That makes it really hard to work with things where there's symmetry, because it clashes with symmetry. Are you using a group action for your movies or not?
No, I'm not, no.
Yeah, that's amazing. Okay.
Yeah, I don't think so. Well, or not that we know of, sometimes there's a group action.
One parameter subgroup models a term order.
I see.
And that's how you slide into the Manon.
I see.
But you haven't told us much about how you slide in, but it doesn't seem to be a group action.
Yeah, I mean, probably, as I said, so Chris Manon, he probably, like, he thinks that when I'm, like, the generations that I'm going to be giving you, they probably will, if you work really hard, you would be able to show that they're Grosvenor. But at the same time, like, there's not a huge benefit to do that, because we have all this machinery and combinatorics that already gives you applications. So why go to the Grosvenor world to
If you can't find a group action, it's not group.
Okay, we haven't tried finding a group action. Yeah. Okay, so oh yeah, and I like this part, and this is more work in progress than the others. Is that we were gonna generalize the notion of a polytope, because one of the takeaways is like we have a generalization of a polytope, and then you can use that to get a variety. Okay, so here, now it's going to get a little esoteric with words. And Megumi no, I guess Chris gave a talk where Lauren Williams was in the audience, and she said that that was a very pretentious word that we're using. So, yeah. So polyptic lattices. And you can search what a polyptic is. But it comes from art. It's foldable, like a foldable piece of art. And I'm not doing justice to the definition, but so you should look at it. So what is it? So it's just what I said before. It's just a collection of lattices where the lattices are connected by piecewise linear maps. So you can always, again, I like drawing cartoons. So I know you can think of having M1, which is connected by a mutation to M2. And this one is connected to M3. Oh, and I guess this, well, I'm doing it in one direction, but it doesn't really matter because they're bijections, and so this is mu2, 1 is mu1, 2 inverse. So this is just what a polyptic lattice is. And so we're gonna, I have two examples. The first one is the trivial one, which I love now, and you'll see why it will be funny later, is just where you have a single lattice. Yeah, there's just a single lattice. And technically, I put the identity there because these piecewise linear maps are also part of the data. And then this one, which is a little bit, this one is interesting because there's one for each rank. And this one will be interesting because it's not trivial. So here I have two lattices that are connected by this piecewise linear map. Okay. And then we're gonna define, well, what are the elements of this polyptic lattice? They are just, so equivalence classes. So you pick an M here, let me call it M1 here, and then that one is gonna be mapping to an M2 here, and that one is going to be mapping to an M3 here, via those piecewise linear bijections. So your element is going to be M1, M2, and M3. Okay. And this will be, I guess this is the most natural of the definitions, that I want to refer to this as charts. So I'm going to have polytopes that are going to be appearing at each of the charts. So you can think of this as an atlas, and you have 3 charts in my picture. This one is going to have 2 charts, and I guess people might not be able to see my cartoon over there. Oh, it's okay. So here, just you have to look if you want to, okay, so I want to get to one thing. Yeah. So I want to define polytopes. So if you think about what are polytopes, well, they're either a convex hull, and I won't go down that path. We do in our paper, but I don't want to go down the convex hull path. They are intersection of half spaces. So for me to tell you what a half space is, I need to tell you like what are linear functions, things like that. And notice that it's tricky because if you start with a line here and you map it over here, it might get folded. And it might get folded in weird ways. So there's some compatibility we need to take care of. And so this is towards that definition. And here I put it in red. This is not the correct definition, but the correct definition, you have to look at the paper. And this is the spirit, like the definition accomplishes this, but it's the correct one. But I think it's too early in the morning to go through the precise definition. So you can just think of a point. So, why am I calling it point? In some sense, because, linear functions are, like inner products with elements. Like every linear function is a like m comma dash is a linear function. So I'm defining what this would be. Okay.
If you really want to upset Lauren Williams, you could just admit you're doing category theory.
Well, yeah. Not exactly, but close.
Terminal, I mean, what's the point, right?
Yeah. It's like piecewise-linear category theory, and so we spent a long time thinking about names, but piecewise-linear or is already overused term, so we had to think outside the box. So what I want to say is, okay, so this part is very natural. So I want to be able to define functions, and so a function is going to be a collection of functions from each of these lattices to z. And one thing, this is very natural, is that, well, if you compose it with the, oops, I guess I have a typo there. This should be, let me fix that typo. I'll use pink. Yeah, that's that. So I'll do it here. The first one should be pj composed with mu ij, should be pi. Not pi, I don't know. That's almost not a typo. Too many i's. Okay. Now, you want it to be linear in one of the charts, so you shouldn't start with something twisted. And then you need it to be a convex piecewise linear function. And that is a little why convex and not concave, or why that condition. It's really what we need for us to be able to define our polytopes. So we're going to define by SP the collection of points of M. And so you should think about this. These are analogs of linear functions. And for the trivial case, yay, that is trivial. The space of points is just homomorphisms or linear maps. And for the other example that I gave you, it just looks like this. You know, it's in bijection, so you can use this to define the functions. So it's some. And using those points, you can define piecewise linear half spaces. And so this is just, okay, I take it that the notion of point is complicated, but the half space, no, like once you have that notion, that's easy. And so this is an example of a half space in one of my examples. So if you see here, in this chart, it is linear, but when you apply the map, it bends, or it breaks, it becomes a broken line. Okay, and so we have the points. Points give us half spaces, and you use that to define a polyptic lattice polytope, which is just a bounded intersection of half spaces, of PL half spaces. And so here I didn't tell you exactly what the half spaces are, but one of them was the one that it was in the previous slide. But here we have a PL polytope in M2. And then by definition, these two polytopes are going to be connected by the piecewise linear map that I used to define the polyptic lattice. And then we define a PL polytope to be integral, or lattice, but we cannot use lattice because then it will be like a polyptic lattice polytope, which would be terrible. So it's an integral polytope. If at every chart you have that it is an integral polytope. So this one is integral, but by the breaking, like since you're bending lines, you might have that in one chart it is integral and in the other one it is not. So this wouldn't be, this is a polyptic lattice polytope that is not integral. Okay, so I want to get, okay, so far I guess the takeaway for now is we have collections of lattices connected by piecewise linear maps. And then we define a generalization of polytopes where at each of the charts you have a polytope and they're connected by these piecewise linear maps. And so I want to get, so remember, what I wanted to say is we start with the combinatorics of a collection of polytopes and we want to go back to geometry, to a variety. And so I want to emphasize, because our construction is going to be mirroring the Toric case. So I mentioned before that polytopes give you compactifications of tori. So how does that work? So if you have a lattice polytope, you have a toric variety, back from my first slide, and that's going to be the compactification of a torus. This is just the torus I don't know if maybe this should be an Yeah, I'm worried about the N versus the R. But anyways. Now, how does one define, like one way to define that toric variety, again, there's the ideal, there's via the polytope, there's the monomial map, this is yet another one. I can give you a presentation for the homogeneous coordinate ring of the variety. This is very nice for Earhart world, because if you notice, it's just like looking at the lattice points at the K dialect of your polytope. So one way to write out your homogeneous coordinate ring is as this sum of these rings. And here, this is, well, somewhat known, but it's actually also connected to Federico's talk, that there's this valuation where you can take Laurent polynomials or polynomials in this ring and map it to piecewise linear functions, where you map it this way. You map this polynomial to, so this is now going to be a piecewise linear function. You map it to the minimum over these linear maps, okay? And now, this is gonna be related to, maybe I should be writing, I did wanna write one of these things on the board. Anyways, so the support function of a polytope then is going to be defined. This is the same support function. Maybe you might have used max versus mean, but it's the same support function that Federico was talking about. So the support function of a polytope is defined in this way.
I think this slide is critical because you're saying a valuation is piecewise linear. And everything in the Grosvenor world is simply linear.
Okay.
There's no cracks and bends. Is that what's going on here? Is that why this is so different?
Well, I don't know. I mean, when you say Grosvenor world, you're talking about going to
Well, for a
monomial
particular
ideals?
problem, even though Lex order is a bunch of different conditions, you can approximate any term order up to a given degree, and you only need up to a given degree to finish a calculation by a weight vector.
Well, I'm
So
not
that weight
sure.
vector gives you the one parameter subgroup, which is the algebraic interpretation of what you've done. But that is linear across the board. It's not piecewise linear. Piecewise linear is mind-blowing by comparison.
I think there are, I don't know. I think we should talk a little bit because
Okay.
I think there are like ways, there are Grosvenor examples for like,
But they're back in kindergarten. This is something more.
yeah, we should talk a little bit. Yeah. Okay, so if you go again, remember I was talking about the Cox-Little-Schenk book that has everything, and if you go through it, you will definitely see this, and you will definitely see another way to describe the chord. I mean, I guess maybe you won't see it in these terms. This is, but this is an easy translation of what we have here. We can use these support functions to, this valuation and these support functions to describe the coordinate ring of the toric variety in this way. So it's going to be the polynomials. Yeah, so the kth graded piece is the polynomials such that their valuation as a function is bigger than the support function of the kth dialect of your polytope. Okay, so this you will find in Cox-Little-Schenk, and this is maybe an exercise, but it is a fact. And so I wanna maybe, do I have time? Yeah, I do wanna write that one down. Okay, I won't. Okay, got it. Yes. Okay. Okay, so now to finish, so we wanna. I guess I have many slides left now, but I wanna like maybe take some points. So here, this is important. So notice one of the beautiful things in lattice world is that you have duals. You have the dual lattice, and so that is important for us to have a good machinery. And so but what is it? What is the dual to this data? So we define the notion of the dual to that data, and we're going to assume that you can always find it. So roughly, if you think about what the dual is the dual. So the dual to M is going to be another polyptic lattice and a pair of bijections that tells you, oh, well, the elements in here are in bijection with the functions or points of the other one, and the elements of M are in bijection with the functions or points of N. And so here we need to generate a semi-algebra. So this is going to be, so this will be important. This is like, remember, we have, in the previous one, we have piecewise linear functions, right? And so piecewise linear functions, they're generated as a semi-algebra by linear functions. So here, we're going to do the same thing, where we're going to generate a semi-algebra by taking this, or an analog of linear functions, and taking minimums and pluses of them. And then we're going to define a valuation to be, now this is why I had this on the board. It should look very similar, right? In tropical world, minimum means like that O plus, right? So this looks just like that, except that now you're not mapping to Z to the N, you're mapping to this semi-algebra. That is a bit exoteric. But it's natural, like it's a natural analog to the linear case. And so at the tropicalization of M is at domain A together with a valuation. So remember, we started with polytopes. We want to go to algebra. And this is important. To go to algebra, we need to have a valuation that goes from your algebra to this semi-algebra. Okay. And add, for the trivial polyptic lattice, we had said that the functions are just linear functions. And the dual itself dual. And this semi-algebra is the set of piecewise linear convex functions. Okay. And so the toric case was what we had before. The coordinate, or this Laurent polynomial ring, is at the tropicalization of the trivial one, and this is the valuation.
You can take a few extra minutes. You have fun.
And then just a quick remark. Well, I mean, for the example, we have that, For the other example, we have that this is the tropicalization. So I won't go into the details of what the valuation is, those details are in the paper, but this is just so you get a sense of like the difference. The previous one, it was this type of thing, and here we have this type of object. And if you're gonna propose a theory, you need examples. So we give for each d comma, for every pair of integers, we give a polyptic lattice together with a detropicalization, and the detropicalizations are gonna look like this.
So, what does the bijection mean on here?
It's just, it's a way to it's just a bijection. So for each element of n, so if you take one of this, you want to obtain a point. So you have to give it. That's part of like it's part of the definition. So if you're gonna say M is dualizable, then you need to be giving a bijection. And so here, I guess, and I guess in this case, like this easy case, the bijection is, of course, how the linear pairing works. How every linear function is given by taking an inner product between an element of your lattice with. Okay, so here, I want to tell you, this is like the punchline. I want to tell you how polyptic lattice polytopes give you compactifications. So you start with a polyptic lattice and its detropicalization. So you have a valuation from A to that semi-group that I mentioned before, semi-algebra, with valuation U, and you want an integral piecewise linear polytope. And it's dualizable, so you're going to have the dual. Now we define the support function of our generalized polytopes. So remember, in this setting we have different polytopes. So if we were in this example, we would have 3 polytopes connected by piecewise linear bijections. So we have a polyptic lattice polytope. So the support function, we define it to be, this is very similar to the other one, right? It's the minimum. The other one, we had the minimum of this type of functions for each of the lattice points in your polytope. So we're just taking the minimum of the points in the dual. And we define a graded algebra. Now here, I wanted to leave this up there, right? It's going to be, this condition is analogous to that. So that's how we're defining this algebra. So our main theorem says that this, if you take proj over this algebra, is going to be a compactification of the original one. So for toric world, we had that the toric variety of a polytope, is going to be a compactification of a torus. And for each, for each chart image of your polytope, you have that the toric variety of that chart image is the Newton-Okounkov body. It's a Newton-Okounkov body of, of this. Sorry, I kept reading this as a toric variety, but no, this is like not necessarily a toric. It's probably not going to be a toric variety. So for each chart image, you have various toric varieties associated to your compactification, and these polytopes are connected by piecewise linear bijections. So, so you have delta 1, delta 2, and delta 3. You have 3 toric varieties, and the polytopes associated to them are connected by these piecewise linear bijections. Okay, so and I guess there's some geometric properties, but I'll go very quickly. This is just a repeat of what I said before. We get toric degenerations for like, there's each of these polytopes gives you a toric degeneration of your x delta, and there's some nice properties. This ring that I constructed is finally generated. The compactification is arithmetically Cohen-Macaulay. If the original detropialization is normal, then your resulting variety is also normal. And if A is a unique factorization domain, then you have a finitely generated grass group and a finitely generated Cox ring. And I can go back to that slide, but I just wanted to advertise this companion paper that if you look at our original paper, there's maybe not that many computations, but in our companion paper, there's a lot of sample computations, and we give a connection to Gorenstein-Fano, and we generalize Gorenstein-Fano polytopes. Thank you.